How you doing tonight? We are in chapter 5 of water and wastewater laboratory techniques, and tonight we're going to be talking about temperature measurement. Most of your lab permits will require you to record your effluent flows at least once a day or continuously with temperature. And constantly in the laboratory, we are monitoring either the ambient air temperature or the temperature of our samples or our standards and our reagents because at different temperatures, water acts differently and standards act differently. And so we want to make sure that we're, paying attention to temperature. So temperature in the book is a measure of the motion of molecules. Molecules that have a lot of motion are at a higher temperature than molecules that are moving more leisurely. Heat is the transfer of temperature from one item to another. There are places where high temperatures exist, but there's little heat. The fringes of the Earth's atmosphere represents one of these places. Temperature is the most commonly determined by quantitating a heat transfer from the object of interest to some measuring instruments. These temperature scales, which is important for you to know, are Fahrenheit, Celsius, and Kelvin. Um, and you need to know, well, flip over um, on page 94. Those are the standard equations for converting Kelvin to Celsius or Celsius to Fahrenheit. You need to know that as a water and wastewater operator for your test to know how to convert Celsius to Fahrenheit. Um, it's important to know that the internationally recognized fixed temperature reference standards are the boiling point of oxygen at 1 atmosphere of pressure, the boiling point of water. The official temperature measurement standard is the platinum resistant thermometer. And so you can see at the bottom, um, where all those on the comparison of the Kelvin, Celsius, Fahrenheit temperatures. And so you can see where it is at absolute zero, at the water's boiling point, and then most importantly, and what we're going to talk about tonight a lot is water at the ice point. Um, the main parts of a liquid and glass thermometer are the bulb, the stem. The stem may include an auxiliary scale for calibration of the ice point, a contract chamber, an immersion line, and the main scale. So you can see on the bottom there just all the different parts of a liquid in glass thermometer and just knowing kind of how they work, how um, you know they're measuring is important for operators. All liquid in glass thermometers rely on the expansion of the liquid column with increased temperature. So some of yours, it talks about some of them may be mercury filled, and some of those, I believe they call them organic liquids to be filled. The glass thermometers come in three designs. So you have your total immersion, partial immersion, and complete immersion. Um, you know, Knowing what type of thermometer that you have and knowing whether you need to totally immerse that in the liquid that you're trying to um, sample or partially, submerge that. On page 96, there's a picture of thermometers. We would keep those in a like where we keep our samples in the refrigerator. Those bottles kind of act as a heat sink. So when you take it out to read it, it doesn't change automatically. It takes a little time for the um, for it to change. It's important to remember that glass thermometers are fragile instruments, especially for the NIST certified thermometers, and they can be quite expensive. It's funny, well, not funny, but I just broke a thermometer last week, and one of the samplers, I was working on a sampler. So these are pretty delicate, and the bulb can be perhaps the most subject to damage. In the lab, you may have on 98 temperature indicating strips. They are based on color changes of the liquid to crystal spot with changing temperatures. They are available in either single temperature indicating spots or multiple spots on the strip of plastic. So you can see um, what we have there in terms of indicator strips. Once again, it talks about on page 99 how liquid and gas thermometers work. It highlights that the bulb there is easily broken. Um, you may have to, it says another technique applicable for organic liquid filled thermometers is to gently heat with your hand the glass capillary at the spot of separation and carefully tap the stem. I don't know if you've ever had a thermometer where the liquid, the black, is no longer together. And so there's several steps on page 99 that talks about how to get those that liquid thermometer, especially if it's set in a laboratory drawer, how to get that black indicator back together. The calibration of a precision thermometer, regardless of type, should be checked at least annually. Calibration check at the ice point of water is the typical procedure. And then it tells that typical procedure. You get a suitable ice bath. It's formed from shaving ice. The slurry is compressed. The excess water is decanted. The bath temperature stabilizes after 15 to 30 minutes. The thermometer is immersed at the appropriate point and temperature is determined. The auxiliary scale is provided for the calibration checking on thermometers that do not include the ice point on the main scale. The difference between the point zero Celsius mark on the thermometer and the actual reading in the ice bath is the calibration correction. Many laboratories certification programs provide an annual calibration check of each thermometer used in the laboratory against an NIST traceable. At my laboratory, we do a calibration check for all our thermometers, and then we'll put a flag up top, and the flag will say plus or minus, how many degrees, so that we know, uh, how off uh, that thermometer we're using is compared back to the NIST traceable. You say, well, why don't we just use all NIST traceable? It's because of cost. So, if we have one NIST traceable or we get that done annually or semi-annually, then we know that is within the tolerance of ranges for thermometers, and we can proceed from there. So I hope you enjoyed the chapter 5, and I will talk to you later.